Hello everybody. Today we are going to start a new topic which is called feature point detection, or the simplest version of it, corner detection. After the corner detection, we are going to look more into more complex features such as the Sift features if we have time. So the last time, remember, we looked at two types of edge detectors. The first one was first derivative based edge detectors, such as the Sobel or the Previtt operators. And then we looked at the Kenny edge detector, which uses one of these operators first to get the gradient images, X and Y gradients. Then it obtains two types of images. One is the magnitude image, the other one is the orientation image. Then it does the maximal suppression step, non-maximal value suppression step. After that, hysteresis thresholding, and you get your edge results. And we said that maybe instead of using this kind of algorithms, we can take the second derivative of the images. That was the Laplacian of Gaussian. First, apply a Gaussian to get rid of the noise, or eliminate noise as much as possible. We cannot get rid of the noise all the time altogether. And then we apply first and second derivatives, and we get two images, of course, and we add them together, and then we count the zero crossings. That was we do. So that was the Laplacian of Gaussian approach. And if we do that, we get this kind of a result. Remember, with the Laplacian of Gaussian approach, zero crossings, there are two parameters. One is the application of the Gaussian sigma, the value of the Gaussian, the parameter, how large it should be, okay, how strong of a smoothing kernel we are going to apply. And the second one is the slope of the zero crossing line. And if it's a small thing, then we will leave lots of, we are going to see lots of details, etc. So that was kind of a summary of what we did last time. It looks nice, either the Kenny or the zero crossing operators, Laplacian LOG operators. It looks nice, but still we have some problems around the corners. Okay, so when things near get the corners or the junction points, like this kind of a point or that kind of a point, we don't get good results. Also, our results depend on the Gaussian that we apply. Here is a tricky image. The image is tricky. Usually people have lots of problem with this kind of images. They think that this is kind of a spiral, but it is not a spiral actually. These are all circles. Let me try to draw it. See, this is a circle, okay, and this is another circle. Okay, so human psychology is very different. It uses lots of local operators. Then by applying a bottom-up approach, it tries to reach a top-level conclusion. But it doesn't always work. We go into this kind of illusions. We think that it's a spiral, but it's not a spiral actually. But we cannot make our brains think otherwise. Anyway, let's look at this image. Let's try to do the edge detection. Okay, if I do the edge detection without applying a very large Gaussian, I get such an image. which is as expected. I get all the details and everything. But if I apply some Gaussian, large Gaussian, I get this. Okay, so it is looking at, look at this now. Okay, this part is very different than this part, right? Maybe the outer parts are similar, but the inner parts are getting very, very different. Why? Because the inner parts has lots of details. If I increase the Gaussian amount, then I started getting this kind of effects. Okay, so this scale thing is important. So by changing the scale, okay, by changing the scale, I am getting different features. And human eye, I mean, as the theory goes, human eye is sensitive to some features based on some of the scales. For example, when you look at this one, I kind of see the circles. Okay, these are the circles. But if I do this, everything is starting to become like spirals again. There are no spirals, but I am seeing spirals like there. Okay, so you can do the similar stuff with all kinds of other images. For example, again, there are no spirals in this picture, but we think that it's a spiral because of the pattern inside these squares. And this one, for some reason, looks like all squares, right? There are no squares in this picture. They are all circles, but we think that they are squares. Anyway, and this one again, these are all, it's kind of hard to believe, but yeah, these are all circles. Okay, these are all circles. Anyway, the scale is important. Scale is important for us, and scale is important for the computer vision techniques too. So edges, they depend on the scale a lot. So by applying different amounts of Gaussian filtering, we get many different results. Many different results. And this is fine for some cases, but for many cases, we should be able to extract features that are independent of the scale, independent of the application of the Gaussian. That's what we are going to do today. Some other stuff, division, everything in this, all the lines in this picture are parallels, but for some reason we don't see them as parallels. For example, this line here, this line here is parallel to this line. See, these are parallel, but we don't see it that way for some reason. Okay, so today we are going to look at this. We did the filtering, we did the edges. Now we are going to do the corners. After the corners, we are going to go to more complicated features such as Sift. Okay, so the correspondence between images are very important. I like to say this part of the image corresponds to this part of the image. For example, these letters STOP, stop and stop, they correspond to each other. Okay, once I establish that correspondence, maybe I am going to use this information to recognize the traffic signs. Also, there are other things such as this point corresponds to this point, and this point corresponds to this point. So the correspondence is important, and you will see why it is important in other chapters when we look at more multi-view stereo or motion analysis. Okay, so we do this in many different ways. Sometimes we are going to match points with points. Sometimes we are going to match patches with patches. Okay, but we will be doing lots of correspondence establishment between the different frames, either correspondence between different objects or correspondence between different views of the same scene. We are going to do this a lot. If we are going to match the points of the correspondence points of the if we are going to do the match the points, that's called the points correspondence, then we need to pick those points first. Okay. What kind of other applications? Image alignment. Let's look at these two images. These two images are taken from two different points of the same scene, and these dots are selected as candidate correspondence points. For example, here this one says that I have picked a point here. It's an important point, and this one says that I selected a point here. So if I represent these 2 points using certain techniques, then I can match these. And there are many ways of matching these points. Okay, did you notice that? Did you notice that there are no points at the sky that can be corresponded? Why do you think so? The sky is blue and I don't see any marks on them.
Because it's solid color, no edge.
It has no distinct features on the on the sky, right? It is all blue. How are you going to do the match? Okay, how are you going to do the match? If you are going to match something, that point should have some features that distinguishes itself from the other points around its neighborhood, right? So these distinguishable points are important. So image alignment, if I do the image alignment between these two, I can maybe stitch them together, or maybe I can do the stereo triangulation to estimate the depth of each point. Okay, so image alignment for stitching or for 3D reconstruction, or sometimes motion tracking. Okay, I am this is far away, right? This is closer. I am moving away from the structure. Okay, I was close, now I am far away. So I have I am taking these pictures using a video camera. So if I establish these correspondences between the video frames, then maybe I can do some motion analysis. Okay, so other stuff is indexing and database retrieval. You will say that you ask Google, did you see this picture before? And Google says, yeah, yes, I have seen it. Yes, I have seen it many times. It is here, and here. For that one, you need to extract lots of features, lots of distinguishable features from the image, and try to match it with all the images that you have. Okay, so finding these kind of points on images have many application areas. Same scene, I took 2 images of the same scene, but I moved my camera, I rotated my camera a little bit to the right. First I took this picture, then I took this picture. As you see, I rotated my camera to the right a little bit. Okay, so panorama stitching, I like to move these things together so that I have a wider field of view picture. That's what I like to do. Okay, that's what I like to do. So what you're gonna do is, so maybe you already know how to do this, right? You did a similar stuff. What you're gonna do is, you would say that you would mark it. You would say that using your mouse, you already did this with your homework number 1. You will say that this point corresponds to this point, and then this point corresponds to this point, and then let me use a black color, and I like to use somewhere in the middle. Yeah, This point here corresponds to this point. 3. Let me pick a fourth one. I think I am going to use the blue again. Here, this blue corresponds to this one. Okay, so 4 points correspondences I have. Now I can define a homography, right? When I define the homography, I can transform this image into the space of this image. Now I can stitch them together. I can put them together. So what am I going to have is like something like that. Where is my transformed image? No, I don't have it. No. Do I have it somewhere? No, I didn't put it in here. Okay. So the homography is going to give me the transformation between this image space to this image space. So I can put them together into the same picture. Okay. So who is going to give me those points? Okay. You can mark it with your hands, but that's not preferable because that requires lots of human intervention. We don't like it. So let's do it automatically. Let's extract those points and find the correspondences automatically. So this is what we do. Okay. We do the detection first. We find a set of distinctive key points. These are called key points. Okay. These are key points. So there are some very nice key points found here. For example, the points around the peaks. Remember the first points that I marked around they were around the peaks because they are easy to find and they are easy to mark. And computer vision algorithms kind of are doing the same thing too. Okay, and then you don't see any key points at the sky because there is no distinctive about sky. It is all blue, and you see others here. Okay, so once you find these points, okay, of course, when I say that I found a key point here and there and there, I don't know that this key point corresponds to this one. I don't know. I found them separately. I run my key point detector on this image, then I run my key point detector on this one. So this one says that I have 50 key points. This one says that I have 60 key points. Now it is up to me to make the matches between these 50 to 60 points. Okay, I am not done yet. For that, what I am going to do is I will represent each feature point as a vector. Okay, I like to represent each feature point as a vector. For example, this would be what I do. For this point, maybe I can take this 5 by 5 image around it. Okay, so the total of 25 pixels. Total of 25 pixels. So these, I would say that this is a vector of 25. Okay, this is a vector of 25. This vector represents this point, and for each one I can come up with a vector of 25 to represent that point, and I would do the same thing here too. So I would represent each point with a vector. This is not a very good way of describing that point, but that's something that I can do. There are many good ways of representing the region around it, around each descriptive point. For now, let's assume that I am using the original pixels. Okay, what would be the bad part of representing each key point with the image area around it? What is the problem? I said that for each point, maybe I can represent it with the 25 pixels around it. But later I didn't like it much. So why do you think that I don't like this approach?
Mouse 10 key point is not here in last image.
Because the key point is not here in the left image.
Yeah.
Well, I mean, it doesn't matter. Okay, here I do here. This one is in the other one. Representing each point with image pixels around it is not a good idea.
It is memory inefficient and overlapping pixels. We need to store overlapping pixels over and over again.
Well, 25, the vector of 25 is not a bad size to represent a key point actually, and the ones that we are going to see will be much larger. Maybe I should ask this question in a few minutes. Once I find the descriptor for each key point, okay, each of these dots is a key point. Okay, they are distinctive points that I can detect. Then I come up with a vector that describes these key points. That's called a descriptor. And then I do this matching. Okay. For each point, I have a 25 of size vector. For each of them, I have a 25 vector. So what do? I take the difference between these two vectors. How do you take the difference between the vectors? It could be absolute difference or it could be the Euclidean distance, right? You would say, let's say, x1 is this one, okay? X1 is this one, x2 is this one. So how do you measure the distance between this x1 and x2? You would do x11 minus x12 square, or maybe I can do all of them from 1 to 25, right? So take the difference and take the square and add them up. That will give you the difference between these 2 points. If the difference is so close, then I would say that these 2 points match. Otherwise, I would say these 2 key points do not match. Okay? So I am asking the same question again. What is wrong with representing a key point using the image area around it?
We lose spatial information.
We lose what?
Spatial information.
No, we don't, because I am not changing the order of pixels. I mean, this one, x1 2 and x1 1, they correspond to the upper left corner of the 5 by 5 region. Anybody else? It is bad for the matching actually. What is wrong about this approach?
It can repeat.
It can repeat. Yeah, you are saying that for the constant regions the matching doesn't occur, but for the constant regions I don't pick any key points anyway, so you don't see any key points on the constant regions. There are no key points coming from the sky, right? The problem could be this. The problem could be this. I know that this point corresponds to this green point, right? So the 5 by 5 here and 5 by 5 here, they are supposed to correspond, but as you see, these pixel values are so different. One of them is a bright image, the other one is a dark image. How is this going to work? Right? Is that correct?
Yes.
That's one thing. The other thing is this. Maybe it is related to what Efkan said. Suppose this is a nicely taken image actually. I just rotated my camera to the right a little bit. Let's say I am rotating my camera around in the axis, both to the right. Also, I am rotating my camera to the 45-degree angle, something like that. So the mountain skyline will be something like this. Oh, it doesn't work. Let me use the okay. It's going to be like that. Okay. So this is the mountain side, and the upper side will be the sky. So if I rotated my image, matching these 5 by 5 images is not going to be good because one is a rotated version of the other one. Doesn't work. So we need to be careful about what we call a key point first. Also, we need to be careful about how we describe that key point. Okay, so we will be talking about many of this stuff today, and unfortunately we are not going to come up with the perfect solution, but at least we will have a good way of discussing what is good and what is not with our key points. Okay, so the goal of the key point detection is it should be distinctive. Okay, it should be distinctive. I cannot say this is my key point here because it is not distinctive. I can match this point with thousands of points in the other image because it is not distinctive. Okay, I like to be able to reliably determine which point goes to which. Okay, so it has to be distinctive. Also, it has to be repeatable. What do I mean by repeatable? If I detected a point here, okay, it is distinctive, I detected it, I should be able to detect the same point on the other images too. You will say that I detected 4 distinctive points here, and then I detected 4 other distinctive points there, but these points are not matchable, right? So this method of mine is not repeatable. I like to have repeatable key points so that I have a chance of matching them. Okay, I have a matching them. So there should be many candidates for this image and many candidates for this image, and I have a good chance of matching them between themselves. Okay, good. So this distinctiveness, repeatability are very fundamental fundamental criteria for our key point detection. We do this key point detection for object detection actually a lot, also the key point descriptors. For example, there is a very successful key point detector and descriptor. It's called Sift, and we are going to look at it. Sift runs on this image, and it says that I have found 1, 2, 3, 4, 5 points, key points, and these are the centers of it: center, 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 and center. Okay. When I do the descriptor of these points, I can come up with these 5 patches, image patches. And note that these Sift descriptor has some orientation in that too. Okay, a key point has some orientation picture in it. Okay, so this image corresponds to this one, but see, their orientations are different. so it knows which side is up. The same technique is used on this image. As you see, the objects are the same. There is a toy truck in there. The objects are the same. I find this key point, this one and this one. I know this one corresponds to this one. It one corresponds to this one, and this one corresponds to this one. Okay, so by matching these kind of key point descriptors, I can do the object detection. I will say that I know this object. This is the truck that I have seen earlier. Okay, so this is how you do the object detection using the key points, distinctive and repeatable key points and the descriptors. They should be invariant to geometric variation. There is a geometric variation between these two, right? What is the geometric variation? It is the rotation and the scale, right? The truck is rotated. Also, truck is a lot smaller. So translation, rotation, scale, and perspective is different too. This is taken from far away, more like an orthographic projection. This is more like perspective projection. And then the appearance. Okay, this one is darker than this one. As you see, the back part is the darker than this image. So whatever we find, it should be robust against these kind of geometric and radiometric variations. Okay, good. Also, another thing is compactness and efficiency. Okay, these two things, okay, distinctiveness and repeatableness are good in theory. We should be distinctive and repeatable, but as engineers, we should be careful about compact and efficient ways of doing this. Why? Because we are going to run this on a computer system which runs on a CPU. We don't want to waste our CPU time. We don't want to waste our memory. Okay, and we like to run these algorithms as fast as possible, so that there is a hope of achieving real-time object detection, real-time motion analysis, real-time image retrieval, etc. Okay. And when you are representing points, your representation should not be larger than the whole image itself, right? I have the whole image, and you cannot store data larger than the image itself. That wouldn't be very good, very efficient. So the compactness and efficiency is another criteria for us. Okay, so if you put them together, distinctiveness, repeatability, and compactness and efficiency are the things that we try to achieve with the key point detection, so that we can do those kind of applications. Good. Okay, so I'll talk about this. Find a set of distinctive key points, and okay. So, how do we make a decision on the distinctiveness? I mean, how would you say that? I ask you, who said that? I ask you, why there are no points from the sky? Somebody said that it is all constant. So we would say that it is not distinctive. It is not distinctive. So how we are going to make a decision, and this one is not distinctive. Okay, this part of the image is not distinctive either, or that part of the image is not distinctive either. Okay, so how do we make a decision on the distinctiveness? Okay, how do we know about the distinctiveness features? Okay, so this is what we are going to use. We are going to compare the image against the local neighbor. Okay, we say that if this is my image, if there is a point on the image like that, I will take I will take the local image region around it, and I will compare this local image region with the other local regions around it, like that. Okay, so I will take the original local region and I will compare with all the local regions around it. If they are similar, then that means that that point is not a distinctive point, right? They should be all different. They should be all different. So that's what I'm going to do as to measure the distinctiveness of a point. Distinctiveness of a point. We can compute how stable a location is in appearance with respect to small variations in its position. So if I do the same experiment on this sky point here, wherever I move this window, that direction or this direction or this direction or this direction, I will end up seeing the same color information, right? So this point is not distinctive. How about this one? Take this point. Okay. If I move this point, if I do move this window this direction, would the result be same or different? If I move it in that direction, it looks like, is it distinctive or not distinctive?
It will be different if you go on that way.
If I go that way, it will be different. If I go this way, again, it will be different. So it looks like it is distinctive, but if I move this way, or if I move the red way, it will be the same, right? I am seeing the same mountain edge. So depending on the direction that you choose, it could be distinctive or not distinctive. But the distinctiveness that I want is whatever direction I move, I should get the difference, considerable difference, so that I can call that point a distinctive point. Point. Okay, so this is what our strategy is. Compare image patch against its local neighbors. Okay, so that's the idea of corner detection. From 1980s, after the edge detection work, people said that why don't we use the similar ideas by looking at the local areas? Let's try to find the corners, not the edges. Okay, so this is an edge position, this is a flat region. Okay, if we use this idea on this window, wherever you move your window, you will see the same thing. It is all black. I'm talking about moving it a few pixels. Okay, wherever you move, you will get the same same image. It is all flat, so I wouldn't call this a distinctive point. How about this one? If I move this window left or right, I see lots of changes, but if I move it up and down, I don't see any changes. So this is an edge. But when it comes to the corners, wherever you move this window, it's going to change a lot. So there is a significant change in all directions. That's what we are going to run as an algorithm. So we can, if I ask you to do this, write an algorithm that moves a given window in any direction, and if there is considerable difference between these windows, okay, you would say this is a distinctive point. You would write the algorithm, but that would be a little bit inefficient, and we are going to come up with nice formalizations to define it mathematically more sound way, and we will come up with very compact formulas. Okay, this is what we this is the basic idea. It's called autocorrelation. Correlation, I think we talked about correlation. Autocorrelation is comparing yourself with the shifted versions of yourself. So this is my window. I am going to compare this yellowish window with this blue window. So I am going to shift the window a little bit up, and I'm going to compare it in that direction. And this formula does that actually. So it says that I is our image. Okay, I is our image, and this is image I. Okay, this is image I. At some point on image, there is this point U and V. X is U, Y is V. Okay, this guy says that run this loop, two loops actually, nested loops. One is on X, the other one is on Y. Look at this one. Let me do this. Maybe X is from minus 3 to plus 3. Y is minus 3 to plus 3. Okay, so this loop is going to run how many times? How many times this loop is going to run total? These two nested loops.
6 for 1 and 6 for 1, 36.
Well, you forgot about 0.
Oh, I'm sorry.
So 7 times 7, 49 times, right?
That's right.
So this is going to run 49 times, this loop. Okay, so this is in effect did I just do this right? Shift UV, I'm just doing it in an opposite way. Appearance is there, X and W. Yeah, I didn't do it right. No, this is what I am saying here. Okay, this is X and Y. Okay, let me get this out. Delete and delete. For U and V I am going to do it that way. Okay, U is going to run from minus 3 to plus 3, minus 3 to plus 3. Again, 49 will happen. Okay, around this XY position, I will define a window. Okay, and then this is going to give me that window. That window function could be defined by this box function or the Gaussian. So it should be 1 inside the window, 7 by 7, outside, not 0. Or I can do it with a gradual way of selecting the pixels. So this one, let's look at this one actually. This one says that, okay, around this XY position, you are going to look at this 7 by 7 window. But when you are looking at it, you are going to subtract this X plus UV plus, X plus U plus, comma, Y plus V. You are going to take the difference of it. So in effect, it comes to this. Move it UV, let's say UV is minus 3 and plus 3. And this is a 7 by 7 window. and this is a 7 by 7 window. So what I do is subtract this one from this one, right? And subtract this one from this one, and do this 49 times, and come up with an E number. So E, in this case, I have calculated E minus 3 minus 3. So E minus 3 minus 3 is the difference between these two windows. Okay. Question: what is E00? What is E00? Efkan, I did not understand what you said.
It doesn't change.
So what is E00?
E00 is equal to E00. Is not E0. For example, E00 is in the middle of the window, and value of is equal. It is equal to value of middle pixel.
No, actually it is in the middle of the window, that's true, but what is the value? How do you calculate E00? E00, okay, put 00. Whatever these xy values, doesn't matter. If this is 0, this is 0, then this ends up being 0, right? So it is, if u is 0, then I get rid of this. If v is 0, I get rid of this. So ixy minus ixy, it means that this is 0. 0 times something is 0. So E00 is always 0, right? So for each point xy, I calculate a window, E window. Okay, this E window is 7 by 7, and in the center it is always 0, because it is comparing the same window with itself. Okay. Question: if I get, for a given xy value, I know that the center is always 0, 0. For a given xy value, if all of my E values are zeros, this image is, the 7 by 7 images, all zeros, or very close to 0. What does that mean?
Does that mean we find what we are looking for?
You are saying we did not find what we are looking for. What do you mean by that?
We are looking for a pattern with 7 by 7 camera, and we are looking for the whole image. And if it's 0, it means that no, I think we find exactly we don't.
No. The first thing that you said is correct. If everything is 0, that means that we didn't find what we wanted to find. If everything is 0, that means that we didn't find a distinctive point. Because whatever UV I choose, okay, it is 0, 0 or minus 3, minus 3. All the windows around this blue window is same. Wherever you go, I get the same results when I do the comparison, right? So I must be somewhere like that, okay? I move this window like that, I get 0, 0, 0, 0, 0. Whatever I do, it is all zeros. Okay? Remember, we are taking the difference. We are taking the difference. When you take the differences, everything coming back at 0, that means that this point is not distinctive at all. Right? This point is not distinctive at all. Did everybody get this? To be distinctive, what do you need? Tell me an E window, an E image that shows you a distinctive point. I am going to give you an image of E, 7 by 7 image. I know that in the center it is 0. Tell me what kind of image you like to see to make a decision saying that this is a distinctive point. What kind of image would that be? I already gave you the center point. It is going to be 0. What would be the result at E plus 3 plus 3 or minus 3 minus 3? Would it be large or small? Okay, Mustafa, you tell me. You can tell me. You can say this. Mustafa Cömert.
I think it will be small.
Well, if it is small, then it would be similar to all constant image, all E0, right? If E's are all 0, then that means that I am in a constant region. What would you expect? It should be high, right? In the center, it should be 0. There is no way escaping from it. But when you move away from center, it should be high values. So in the center, it is 0. If I go around like that, okay, each concentric ring is going to have larger values. So the largest value will be around the corners, right? That would be your E image. That would be your E image. This is how you compare yourself with the neighbors. Okay, so what is going on with you guys? Nobody is answering me anything. I am not saying anything. I am not telling you anything complicated. This is simple multiplication and subtraction stuff. Okay, let's take 10 minutes of break. Go drink something. Drink with something with caffeine. Okay, let's be here around 14:38. Okay, let's continue. So this is to find, again, the idea is this. Idea is compare the image patch against local neighbors. So you take the center window, you move around like with in the directions of U and V, okay, and you compare these two windows. If the windows are the same, then that means that window is the same as the neighboring window. So this is not a distinctive point. This formula is for that one. So try all the UV values between -3 and +3, those 7 by 7. And I am going to repeat this for all the pixels in the image. So what would be the cost of this whole operation for the whole image? Let's say I have an image of size m by n, and my UV is going to change from -3 to +3. So what would be the cost of whole operation?
E filter of E channel have to pass from a pixel point 49 times.
Yeah.
Pixel.
So it is 7 times m times n, right?
Yes, exactly.
So this is expensive. This is not easy. This is expensive. And after that, I need to, for each xy, I have this image, 7 by 7 image. I have to compare it. I have to say that this is a distinctive point or not distinctive point. And I'm not going to do that. Okay. So this is a sample output of EUV for an image like that. Okay, so this is not 7 by 7, but how much? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is 11 by 11. 11 by 11 E, okay. As you see, E00 is 0, very dark. And this is E -5, -5. Would you say this is a distinctive point? This XY here, the center. Where is the center? I think this is the center. Do you think this is a distinctive point?
Yes.
It looks like, kind of, yeah. Because why? Because at the center it is dark as expected. When I go out, it becomes light. So especially, what does that mean? What does that mean? This point here, what does that mean?
It means high difference. Like going through there will mean a high difference at the center, right?
Yeah. That means that if I compare this red window with this green window, okay, if I move it 5 pixels up, right, the difference is very high. How about this one? If I compare the red window with this blue window, the difference will not be that high. Do you see the similarity between these two windows? Yeah, they are kind of similar. Red and blue are similar because this is low, but red and green are not that similar. So I need the way of deciding that these two similar windows are similar or not similar by looking at those E values. But again, as I said, this is 11 by 11. This is n by n. This is complicated. This is lots of multiplications. Okay, and we are doing the same thing here. Okay, so let's look at some EUV images. Okay, I'm going to ask you a question. I have this point, and there is this point, and there is this point, 3 points, and A, B, and C. Tell me which one is which. Is this A, or is this A? So they had this nice visualization. They visualize these intensities like a 3D surface. Okay. Tell me which one corresponds to C.
It has to be the third one.
C has to be, let me,
Sorry.
1, 2,
No.
3. What is C? C is 1 or 2 or 3?
I think 2.
Does anybody have any ideas? C is what?
I think 2 as well.
Okay, yeah, C looks like 2. Why? Because look at this one. Let's go to C. Let's go to C. Yeah, here it is. Okay. If I have a window around C like that, if I move it up or down, lots of difference, but if I move it this way or that way, not much difference. Okay, so it looks like it is that way. So if U and V are along this line, it will be all black with very close to zero, but if I move up and down, it will be different. Okay, yeah, that's true. How about A? Which one is A? 1 or 2? So this is C. 1 or 3? What is A? 1 or 3?
It has to be 3.
It has to be 3. Why? Because wherever I move, it is all dark. Okay, and B is going to be this one. Why? Because in B, center is very similar as always, but if I move around, it is all different. So it is distinctive. Point B is distinctive. Okay, so we found our kind of algorithm, but as I said, it is too expensive to calculate this for the whole image, especially if you think that these people are doing this in 1980s. It's not going to be accepted. This is called corner detection by autocorrelation. Okay, and we like to discover how E behaves for small shifts, but this is very small. Window width square, shift range square, and image width square. Okay, so you need to do lots of them, and that's going to be expensive. Okay, so what did I say? I said that you have to compare this how many times? Where is my, yeah, 7 times 7 times m times n. For each of them you need to run this. Okay, this is going to run for all the UV values for all the xy's. There are 7 times 7 UV values for all the xy's, right? But inside this loop, there is 7 times 7 stuff. So it's going to be. I mean, if you include the subtraction operators, you need to multiply this with 7 times 7 too. Okay. So good. That's going to be expensive, and we don't like it. Let's do something else. Okay, we like to find a strong peak here, and we like to do something else, and that's where the Harris corner detector comes in. Actually, you know what? We could have done the same thing with the edge detection, right? We would find these E images, and if we find something like that, and we will call this an edge. Is that true? Yeah, I could that too. Okay, but we didn't do that. Instead, we developed much more compact and reliable ways of detecting the edges, and we are going to do the same thing here. So Harris corner detector tries to perform this operation, whatever I did, autocorrelation, comparing the image patch with the image patches around it. Okay, but it is trying to do it in a much more compact way, much cheaper way. Okay, and it defines this, says that there are three types of windows. Okay, one is a constant window. Okay, so four kinds of windows. Sorry, one is a constant window like sea, like the sky. Okay, so the gray level is approximately constant wherever you move. There is edge windows. Okay, there are certain directions where the change is sharp, but other directions the change is not that sharp. And there are flow windows. Okay, flow window means there are several parallel stripes within the window, or there is a flow. For example, in this image, this part is all 255, this part is all 0, but between that there is a very gradual decrease. So this is all 128, this is 100, this is 200. There is a flow going that way. Okay, this is a flow window. Okay, so if I move left or right, nothing changes. But if I move in this direction, in green direction, nothing changes. But if I move in the red direction, there is a slight change. So this is called flow window. And finally, the ones that we like, 2D windows where there is some form of 2D texture, spots or a corner within the window. So we like to find this one. The Harris corner detector finds this one, also this one at the same time. It is both an edge detector and a corner detector. And this is the basic idea. It is exactly the same thing. I have a, let's say, I have a image, dark image like that. Okay, this part is dark, the rest of the image is bright. Again, this part is dark, rest of the image is bright, and doing the same thing, this part is dark and bright. If I take this window and move it around here, it's going to be a flat region. If I come here and if I move it around, I will not see any change if I move this window along the edge direction. But if I take this window and move it around, even the slightest movement will cause lots of change. And we like to be able to find the difference between this kind of images, this kind of areas, this kind of areas, and this kind of areas. Flat, edge, and corner areas. Okay, that's what we are going to do. And if we do that, we would be successful in finding the distinctive points. Okay, so similar to what I have written, remember EUV, I am writing the same thing here, like DUV, and this is what I am trying to calculate. For a given UV direction, I like to find the difference between this image and this image. And if they come back as same, then that's a flat region. If for all the UVs they are all different, then that's a corner. That's what I like. Okay, so that's what I'm trying to do. So for this part, is going to whatever UV choose is going to produce all 0. For this part, whatever UV choose is going to be all 0. For this part, whatever UV choose is going to be large. For this one, For certain directions it's going to be 0, for the others it's not going to be 0. Okay, good. So let's go back to our calculus knowledge. And do you remember this? You guys remember this?
It's Taylor's formula.
Yeah, Taylor series expansion. What is Taylor series expansion? Taylor series expansion says that if I like to approximate f a plus x, okay, or a minus x minus a, you can use this formula. You will say that fa plus derivative of a, okay, derivative of fa over 1 factorial times x minus a plus this and plus. Where does this go? It goes until infinity, right? We can continue. Usually we don't go to up to infinity. We will say that, okay, for me just this one and this one is okay, because all the rest are becoming so small, I am going to ignore them. Usually we do that, right? So, but that's for one-dimensional functions. Our functions are two-dimensional, right? We are living in a world of two-dimensional images in computer vision world or the image processing world. So what do we do? This is, we say that I plus u, j plus v is equal to iij plus gradient of image in the x direction times u and gradient of the image in the y direction times v, and I ignore the rest. Okay, this was over 1 factorial, I ignored it, and the rest is, remember, if I do the same thing, I need to take the second derivative, u I x x I plus u square, and it will go that way. So it will be I x x second derivative and I plus u square over 2 plus, I am going to do the same thing with the y, but I am not going to do that because this part is going to be small and I am assuming I can ignore them. Okay, so that's it. So if I do this, if I replace this part, if I replace this part with this, I mean this, then I get this one. Okay, so it is ij plus horizontal gradient times u, vertical gradient times v, minus ij. So this one and this one will go. What I end up with is this one. Okay, so square of u and square of ix, 2 times ix iy and uv and iy square and v square. And if we do some linear algebra reorganization, I like to express this like a matrix. I can come up with this formula. Do you understand this? Do you understand where this comes from? I'm just reorganizing this formula, so I made it into a matrix. Okay. This is just for a single uv, right? This is just for single uv. That's it. You guys can I mean, you know how this thing, right? I mean, let's multiply this. If I multiply u times ix square plus ix iy times v. So I'll multiply these two with these two, right? That's what I did. Now I'm going to multiply these two with these two. It is u times ix iy plus iy squared times v. Okay, so I have a two-dimensional vector. Now I am going to multiply this with this one. So u times u squared times I squared. Okay, it is this one. And then I will have these two. Okay, so you know what it is. Okay, good. So if you think this as like given a window, think about a window. Okay, think about a window, 7x7 window, and I like to move this in one direction. This window, one direction. Okay, so I have a matrix in the middle. As you see, this matrix is not dependent on the UV direction. It's very interesting. It is symmetric. Okay, it is symmetric and it doesn't depend on the UV in the middle of this matrix. So it doesn't matter what your UV values are. Okay, to calculate this value, you need to calculate this matrix. You need to calculate this matrix. It is just a matrix that doesn't depend on the UV directions. So you change your UV values, you multiply it with this matrix, it's going to give you this value. It's nice, right? It's a very clever way of expressing stuff. So we made our things a lot cheaper now. To calculate this value, okay, I will calculate these gradients, gradient 2 times, okay, multiply take the gradient in x direction and y direction and multiply with each of them, and you get a 2x2 matrix. And whatever your UV values are, okay, whatever your UV values are, you multiply them and you get your final result. That's a very convenient way of doing things. Can you guys tell me what kind of formula this one is? Let's say I am expecting this to be, for example, 9. Okay, the difference should be 9 maybe. Can you guys tell me what kind of formula is this? If u and v are my variables, if u and I are my variables, ux, ix, iy, ix and iy are constant, of course. What kind of formula is this? Do you guys, what does this define?
Circle.
You're very close, but it is not circle actually. It is more general than circle. Why? Because with the circle, you have, what is the formula for a circle? Ax squared plus by squared is equal to something like that, right? This is more general.
Full square tam kare açılımı.
No, I'm talking about the geometric components in terms of what kind of geometric structure is this? It's not circle, but it's an ellipse, right? It's an ellipse. So we are defining an ellipse here. We are talking about an ellipse, and these 4 numbers, they define an ellipse. Okay, these 4 numbers, they define an ellipse. So we will come back to this later. That's okay. So let's look at this matrix. It's a 2x2 matrix, right? 2x2 matrix. 2x2 matrix. If I multiply this on the left from UV and UV, that's going to give you the difference between the center point, center window, and the center point and the moved out point. That's good. Okay, that's good. So if I like to do the same thing for the whole window, I add them up. I add them up and I multiply them with UV, and that's going to give me the DUV. That's the total. This is the one that I'm trying to find. So that's good, right? Instead of making all those calculations, doing the subtractions and that kind of stuff, by calculating the image gradients in x and y directions, I can come up with this such a small compact 2 by 2 matrix, and this matrix is the essence. This matrix defines everything that I like to do. Okay, good. Let's look at this one. If this is 0, what does that mean? If it is 0, then for that UV value, if it is 0, for that UV value, the difference between those two windows are same, right? The difference is 0 between those two values. That's interesting, right? Why? Because I like to talk about this one. Let's look at this matrix in a more careful way. I have a 2 by 2 matrix. I have 1, 2, 3, 4 numbers, and there is this U and V. So this is a 2 by 2 matrix. I am multiplying this 2 by 2 matrix, 2 by 2 matrix with this vector, UV vector. Okay? I am multiplying this with this UV vector. So what I am doing in essence, what am I doing? I am transforming this UV vector into another space. I am scaling and I am rotating, right? Into this space. So this is a rotation matrix plus a scaling matrix. That's how we see it, right? Do you remember the transformations that we looked at at the beginning of the semester? That's what I am trying to do. So this one says that multiply this 2 by 2 matrix with UV is going to give you, let's say, KL. And if I multiply this with UV, it's going to give you 0. If the multiplication of such two vectors is 0, what does that mean? If the multiplication of two vectors is 0, what does that mean? What does it tell you about the matrix, about the vectors?
In the beginning of semester, we talk about that, and
let me give you one example. 1, 0, 0, 1. Multiply these two and you are going to get what? 0, right? 1 times 0 is 0. 0 times 1 is 0. What you get is 0. So tell me, what does this tell you? Come on, people, you know this. If you multiply two vectors and the result is the dot product is 0, what does that mean?
That's infinity point.
No, we are not in homogeneous coordinates. What do you see? This is what is 1 0 1 0 1. These are orthogonal to each other, right? There is 90-degree difference between them. If you multiply two vectors, and if the result is 0, then that means that these two vectors are orthogonal to each other. You remember it right now?
Yes.
Okay, so these two vectors are orthogonal to each other. So what I'm saying here is that if I multiply this UV with this matrix, whatever it produces, okay, let's say this is K and L. If I multiply this with UV again, it is 0. Then what does that mean? This is such a matrix. This is such a matrix that it transforms this UV, okay, in a way that it rotates it 90 degrees so that its multiplication with itself is producing 0. So that's interesting, and we are going to use this in a few minutes. But this matrix is important because this matrix is telling me about everything the UVs. So this matrix, if I multiply it with the UV on the left and right, okay, on the left and right, okay, is going to give us this the UV values, and this matrix doesn't depend on UVs. That's a spatial matrix, and we should be careful about this spatial matrix. Let's look at this one. Let's say I have a matrix like this. I have a matrix like this. Like this is 5 and this is 0 and 0 and 0. Tell me what this is. What do you see? What kind of window is this?
This corresponds to an ellipse equation, right? I mean, if we place these numbers.
Well, yeah, well, okay, go ahead. I was asking about the image. What kind of image would produce such a matrix?
I thought I could come up with the equation, but no.
Let's talk about the equation later. Let's try to answer my question. What kind of image is this?
Ix R's gradient of X values.
Yeah.
So it's 5. And we know that all total gradient of X values are 5 and other ones are 0. So 0 ones, if we think about a vector,
Yeah.
Gradient vector, total gradient vector, 0 means no change.
Yeah. So it is something like this maybe. If this is my window, on my left it is all bright, on my right it is all dark. So gradient in the x direction is large, but the gradient in the y direction is 0, right? This is what I see. Doesn't matter what kind of UV values are, I can see this one, right? So this one is telling me that, in this kind of case, this one is telling me that, okay, this one is telling me that there is a strong x component in the gradient. If you move it in the x direction, then you would see lots of change. But in the y direction, if you move, then you won't see any change. So this kind of an edge detector, right? I found an edge detector. How about this kind of an image? What would you get with this kind of image? What would you get with this kind of image? You would get something like 0, 0, 0, and let's say 5 again, right? That's true. So again, it's an edge. How about this one? How about an image like this? What would be the matrix here?
I think this time Ix directions total would be 0 because it's and X and Y directions have to be greater than Ix square and Iy square total. Am I right?
Yeah. In this case, they will be they will all be greater than 0, right? In this case, because if I move this way, let me use a different color. If I move this way, there is a gradient, and if I move this way, there is another gradient. So both of them will be high. But that doesn't mean that, well, in this case, the matrix here is going to be 3, 5, 4, 2, etc. So all these numbers will be high. But that doesn't mean that I have a corner here, right? That doesn't mean that I have a corner here. Okay? Because my edge is not along the x and y directions, but it is along at some certain angle. Okay? So remember, this is a transformation matrix. It takes this UV and it transforms into another space, which is rotation and which includes rotation and scaling. And if I like to know what kind of directions are special for this kind of matrix, what did I do? I would do eigenvalue analysis. Do you guys remember eigenvalues? Eigenvectors, eigenvalues?
A little bit.
So it is not a very difficult thing actually. The definition of for a given matrix A, okay, for a given matrix A, there are special vectors V such that if I multiply A with V, you would get lambda times V. Lambda is a scalar. So let's do this. If I have a 2 by 2 matrix, and if I multiply it with these values A and B, I would get, let's say, 3.2 times A and B. What does this tell you? What does this tell you about this matrix?
We turn this matrix to a constant.
We turn this, yeah, it looks like that, right? So in effect, this matrix, all it does is it doesn't change the direction of this vector, right? It doesn't rotate, it just scales it. So this direction is special for this matrix. This vector direction is special for this matrix. It just doesn't rotate it. It is not a different vector anymore, okay? It is the same vector, it is just scaled up or down. It got larger or maybe smaller, okay? So this is the eigenvector for this matrix, okay? Eigenvector for the matrix. Sometimes we write it this way, sometimes we write it this way. It is exactly the same thing. That's the meaning of eigenvectors. So that's what I am going to do with this matrix. I am going to take this matrix and I will ask, what are the special directions for you? Okay, if it says that my special direction is this one, to the left or to the up, okay, to the diagonal, then I will say that, okay, there are special directions for this matrix, and these are the directions, and that's what I'm expecting my edge directions and corner directions are. Okay, so that's what I'm going to do with the eigenvalue analysis. Okay, eigenvalue analysis. it means that I need to find a direction out of this matrix that doesn't change the direction of the matrix multiplication. That's going to be very special directions for me. I think I will. Okay, so that's it. That's the formula that we have. UV times this 2 by 2 times UV constant. So as I said before, this defines an ellipse. Okay, and it turns out that if you decompose the C into rotation matrix, the inverse of the rotation matrix, and it will be diagonalized, and these are my eigenvalues. These eigenvalues correspond to the diameters of the ellipse. Okay, but it is like 1 over square root of lambda. Okay, so larger these values, smaller the ellipse size. Okay, smaller the ellipse size. And if you do the eigenvalue analysis of this matrix, that will give you both these lambdas, okay, and it will give you the important directions for this matrix. And those important directions will be your corner directions. Remember, corners are like that. Okay, this is my corner. There are two directions. One is this direction, the other one is this direction. For an edge image, there is only one important direction, that is this direction. For a constant image, there are no important directions. You will not find any eigenvalues or eigendirections, eigenvectors for constant images. Okay, for edge images, you are going to find only a single direction, which is the only available eigenvector. For this one, there are two eigenvectors which are important. Okay, so that's what I mean by we don't need to calculate all those m by n times 7 times 7 times 7 times 7 calculations. All we need to do is get this 2 by 2 matrix and do the eigenvalue analysis. And if you have just a single eigenvector, that means that you have an edge. If you have two, then you have a corner. If you don't have anything, then you then have a flat image in your hand. Okay, let's say I have an image like that. Let's say this is a 100 by, no, not 100. Let's say this is 20 by 20 image. This part is dark, bright. Okay, if I take just this part of the image and calculate that C matrix, 2 by 2 matrix, remember, 2 by 2 matrix, and if you try to draw the ellipse here, the ellipses will be like dots. Why? Because remember the radius of the ellipse, it was 1 over square root of lambda. So if the lambda is large, the ellipse size will be small. But when I am here, there is a corner, right? When I am here, it said it will be a large ellipse. Why? Because lambdas are so small and they are equal to each other. Here, ellipse is very elongated like this. These are ellipses. Okay, one lambda is large, the other one is small, and here ellipses are like this. Okay, so what I mean at the end is, if somebody gives you a image patch, 7 by 7 image patch, or 5 by 5, you calculate gradients along the x direction and y direction for each pixel, and multiply them with each other and add them, multiply them with x and y's and add them together, you get a 2 by 2 matrix. And you calculate the eigenvectors of that 2 by 2 matrix, and the eigenvalues, look at the eigenvalues. If the eigenvalues are, both of them are large, then that means that you have a corner in that image. If both of them are small, close to 0, then that means that you have only an edge in that image, and none of them are large, then it's a flat image. Okay, so this is how you do the corner detection with the Harris corner detection algorithm. Let's look at this algorithm. Okay, so this is your image. You see the image, right? The Harris corner detector says that these are the corner positions. Lambdas are large at these positions. It is not finding them perfectly because there is noise in the image. Doesn't matter what kind of intensities you have, you'll find those corners. Okay, so the algorithm is, if the area is a region of constant intensity, both eigenvalues will be small. If it's an edge, there will be one large, one small eigenvalue. If it contains edges, okay, 2 or more orientations, there will be 2 large eigenvalues. Okay, so this is the algorithm. This is a very compact way of doing the same thing. C is a corner score. If both of them, let's look at this one. If both of them are large, okay, this multiplication will be large minus alpha times lambda 1 plus lambda 2. This will be a large value, but it's not going to be as large as the multiplication. Okay, so I just add them, and this alpha is a small value, actually, like this one. So C will be large. Let's say I have one large and one small, lambda values. Well, in that case, C is going to be smaller than 0. Okay, it's going to be smaller than 0. Why? Because one of them is large, the other one is small. If I multiply the small value with the large value, it is going to be small value. But if I add them together and take the square of it, this part will be larger than the first part. It's going to be negative. So if C is negative, you have an edge, either this edge or that edge. If C is very close to 0, then it's a flat region. So all you need to do is just calculate the C value. If C is large, okay, greater than 0 and large, then it's a corner. If it is large and smaller than, if it is smaller than 0 and it is away from 0, then it's a corner edge. If it is around 0, then it's a flat region. That's what that guy Harris said in 1988. Okay, and they did this experiment on this. Okay, tell me, where would I find the corners on this image? Where are the corners? Tell me the corner positions. This eye is not part of the image, of course. It's the name of the image. Tell me the corner positions. What was the definition of an edge for us? What was the definition of the edge? How do we define the edge?
Different of pixel values
in the neighborhood, right? I mean, if the pixel values are different in the neighborhood, then we call that an edge. Sudden changes in the intensity. That's why all the points around here are edges, right? All the points around here are edges. Okay? How do we define the cornerness? What is a corner?
Intersection of edges.
No, we did not define it that way. Maybe your definition is good, but we did not define it that way. How did you define the corners?
We said that.
We said what?
We said that different volume difference between more than one directions.
We said that, yeah, we take a window and move the window around. If we see changes in any direction, we call that a edge, right? We call it a corner. So I don't think that this is a corner. I don't think that this is a corner. I don't think this is a corner. But I think this will be a corner. Why? Because if I move this in any direction, it's going to respond. Okay? So I expect that this will be a corner point. Also, this will be a corner point too. Right? If I move it left, right, up, down, it's going to change, and corner point here. Corner points. These are the corner points. Corner points. Corner points. Okay? And this one is a corner, corner, corner. Okay? So these are things that I see as corners. Okay? So to be able to calculate the corners, what do I need? I need to calculate the remember our ix square, iy square, ix, iy, ix, right? This is what I need to calculate. So I calculated this one, ix, gradient in the x direction, gradient in the y direction, I calculated, and then I take the magnitude of it, I take the square of it in the x direction, and I take the square of it in the y direction. Okay, and this is the multiplication of ix and iy. Good, I did that too. And then I apply some Gaussian to ix. I apply some Gaussian iy. Okay, I did that too. And I apply some Gaussian to this ix, iy. And then I run this formula. Okay, this is the formula that will give me the C value. Okay, so the C value is going to be large for corners. It will be less than 0 for edges. Okay, as you see, this is what I get. Remember, the first one is the first one, the original image, and this is the final image. People have found ways of calculating this in a much faster way. They take the determinant of m, okay, determinant of m, then the trace of m, and minus alpha. that corresponds to the C value. So instead of doing all those multiplications, I need to calculate all these images, okay, and do this calculation, determinant of M, trace of M, and the rest is just the subtraction. I think I'm not going to give a break. I will continue. I will finish up. I will quit early today. Okay, so this is the corner detection. It looks like it is working fine. It behaves a little bit weird here. Okay. So tell me, why are these places black? Can you? I know that bright spots are large C's. These are the C values, right? Bright spots are large C's. How about those black parts? What does the black mean?
Well, they were just was an edge.
They were what?
They were just was an edge.
Yeah, so where is the blackness come from? Where is the blackness come from? So what kind of values would I get for C? Can C become negative?
In early lessons, while we translating the derivative of image, we we map negative numbers to 0 to 128.
Yeah. So C can be negative or positive. If it is negative, it's an edge. If it is positive, it's a corner. If it is around 0, it's a flat region. So we cannot show negatives in the images. So what we do, we map the negative values to 0, right? We map the 0 values to 128, and we map the very positive values to 255. That's what we are doing here. So very negative values are black. Those are the edges, right? Very positive values are 255. Those are the corners. The rest are 128. That's why nobody has asked this one. That's why IX and IY, these are all either the small values are zeros and large values are large, because if you take the square of this one, there are no negatives. IX and IY, they contain both negative and positive values. This one and this one, they don't contain any negative values, because it's the square operation. Okay, so this is an example. I take this image. Okay, I take this image of a toy. I take this image and I find the Harris corner detector points, and I take another image in a different direction. I rotated my camera, okay, and my lighting is different. See, there is a reflection here. I don't see the reflection there. Okay, so the lighting is different. The shadows are different. I am trying to see if I can get the same corners from two of them. Okay, so these are the results of the C value for each point. So I think red means high C values. Okay, red means high C values. Blue means negative C values, I guess. Okay, so I calculated the C values for this image and this image. Okay, and how do you find the corners? How do you find the corners out of this image? For example, here, let's look at this one. there is a very large region. Let me use a different color. What kind of color am I going to use? I think I'm going to use this one. Okay. There is a large region. It is all red. That means that it is all large C's. So how am I gonna decide which point is the corner?
If it's we talk about that if C is near 0, it has to be edge. So it can't be an edge because values.
No, well, all of them inside this green curve that I have drawn, they have large C values. Their values are all large, much larger than 0. But I need to make a decision. I mean, you cannot say that this is corner, this is corner, this is corner. The problem is this. The problem is this. Original image, right? Okay, let's take the original image. If I take this window and run this algorithm, calculate all those x gradients, y gradients, and multiplication, do the lambda stuff, you will get a large C value. But if I do the same thing here, again you are going to get a large C value. But the largest will be with this window right in the center. So you cannot choose a threshold saying that if the threshold is above something, then I am the corner. So how are you going to make this decision? All of them are telling you that okay, we are corners, right? They are large C values. So how are you going to make that decision? We have seen this problem in the edge detection, in the Ken edge detection, and we found that they suggested a very nice solution for this, and there is a name for it. Remember, there was a problem with the very thick edges, and we didn't like the thick edges. What did we do to eliminate the thick edges with the Ken edge detection? What was the name of that step? Eliminates the thick edges.
Gaussian?
No.
Non-max suppression.
Non-max suppression, yes. What is non-max suppression? You compare yourself with the around. If there are other pixels that have the larger values, then you are not an edge, and I'm going to do the same thing. I will say that inside this region, this one has the highest C value. So this is the corner. The others are corner, can be considered, but if I have this one, I wouldn't call this a corner. So I find the corners like that. Okay. So these are the places where C is larger than some threshold, because what did we say? C has to be larger than 0. Okay, and then I would run local suprema, non-local maxima suppression, and we would get these. Do you guys see it? I think this is here is the head of the giraffe. like that, right? Yeah, like I think this is better. Okay, good. So these dots here, these red dots, I am making them green, are the detected corner points. And let's try to see if I have the same stuff there. This one, yeah, see, this one is, I found 3 correspondences, maybe this one. And let's look at the, okay, good, see, this one and this one is the same. How about these? Yeah, there are some nice points that correspond to each other. Okay, but many of them will not be, for example, the ones there, they don't correspond. Okay, so if I like to correspond these 2 points together, what I need to do is I need to test it. Does this equal, is this similar to that one or not similar to that one? Okay, so these are the corresponding points. I think I had a nice image somewhere. What happened to my ellipses? Come on, I need to find it. I think maybe it is on the web. There was a very nice picture that visualizes those ellipses. Where is corner detection and ellipses images? It just visualizes each point with the corresponding ellipse. That's not it. Many of these slides are my slides. I mean their slides, but come on, that was very nice image. Where did it go? No, I couldn't find it. Yeah, maybe this one. It is not exactly what I am looking for, but oh, I know where it is. I know where it is. Okay, I'm going to find it. Where it is. I think I took most of my material from these slides. Some of them I removed, some of them are there. But I should have included this part. This is edge detection. No. I am talking about corners. Yeah, okay, it is good. Okay, good. This one. What I am meaning is this. So for each point, they run this one, C. Remember, while calculating C, I have 2 lambdas. If the lambdas are small, that means that 1 over square root of lambda is going to be large. Okay, so the size of the ellipse is going to be large. So let's look at this part. As you see, in the center, this is a corner point. So lambdas are large. Ellipse has to be small and it's circular. Here, these are not corners anymore. These are elongated ellipses. These are kind of edges. So there is a corner here. There is a corner there. Okay. There is a y. Okay, my interface now does work. Yeah. There is a corner here, but these are all edges. You see, these are all edges. So it is showing me both the direction of the edge and whether it's an edge or corner. That's why the Harris defined his method as a corner and edge detector at the same time. Okay, any question about the Harris corner detector? Nobody has asked me how do you match these two, because there are at least 50 points detected corners, and there are maybe 50 there, maybe 100, I don't know. So how are you going to match this corner with this corner? Does anybody have an ideas?
Can we cluster the patterns and see the pattern, match the pattern?
What do you mean by pattern?
Like the middle tree you just pointed. At left it looks like a triangle.
Yeah.
At right it's a triangle, but it's rotated. But
Yeah.
it's just a scale issue, I think. Like if
rotation and scale maybe, but mostly rotation.
But pattern is same.
Pattern
like
is same, yeah.
And horns.
Yeah, maybe remember what I suggested at the beginning, and later I didn't like it. Take this window, 5 by 5 window around it, and compare these windows. Maybe I could do that, right? But that's not going to work because these are rotated. That's not going to work. Maybe I can do this. Take this window that's 25 pixels, right? And make a histogram. Right? How many pixels have value of 0? This many. How many pixels have value of 1? This many. How many pixels have value of 2? This many. Okay? This is going to be an histogram. And I will do the same histogram here too. Okay? Since there are many blacks are going to be like that. So this histogram thing is independent of rotation, right? Is that true?
Yeah, it will be very simple.
Yeah, so maybe I could use histograms. That will be a lot of help. Okay, so I need to come up with ways of describing these points. That's called the key point descriptors. Key point descriptors. Okay, finding the key point is a thing. Okay, it's difficult. Describing it is another difficult process. Okay, so far we found the corners. I didn't tell you anything about how to describe it. We can come up with ideas, but each one has their own problems or advantages. For example, the histogram stuff is robust against rotation, but it is not robust against scaling, right? Scaling is going to cause some problems for the histograms. Okay, that's why we have this next section. We have other ways of finding these points and giving some descriptors. One of the most famous one is the Sift, scale invariant feature transform. So scale invariance is one of the main ideas of Sift. Okay, it defines both detector and a descriptor, and it kind of extends the idea of Harris corner detector, both in terms of detection and description. It's an old method from 2004, okay, and it is patented. Since it is patented, you will not see its implementation in standard Opencv. You need to load some extensions for Opencv. Instead of Sift, Opencv mostly uses Surf. Okay, so but before doing that, before going to do that, let's look at the Opencv documentation. Okay, and corner detection. Let's see the Harris corner detection. No, I don't. No, not tutorial. Let's go to the. Let's go to the documentation directly. So Harris corner, edges, corner, and blobs, and you remember this one. This is the correlation stuff. Okay, and Taylor series expansion, and this matrix is a special matrix. Okay, and if you do this, determinant of m minus k times trace of m is going to the c value. These guys call it the r value. K is a constant, 0.03 or something like that. Okay, so in this case, do we have examples down there? Yep. Okay, so these are the corners found by this algorithm. Of course, I think they set the threshold to some high value. So zeros, okay. Corner Harris, let's look at the documentation of it. I think it will get the, okay, source image, destination output array, okay. Block size is the neighborhood size, 7 by 7, etc. And k size is it is for calculating the gradient, it is using the Sobel operators, remember. K is the size of the Sobel operator. And k is another k is Harris detector free parameter. Remember that parameter, k times something, that's 0.0 something. And border type is the, what would I do when I come very close to the border? Because near the borders, I need to define differently. I need to behave differently. Okay, so it will give you the image to store the Harris detector responses. So this one is going to give you an image of R's, and when you make a threshold, you're going to put your results in there. Okay, good. And this one is going to calculate the corner mean eigenvalue. What does minimal eigenvalue of the gradient matrices for corner detection? Minimal eigenvalue of the covariance matrix of derivatives, that is minimum of it. Not the maximum, but the minimum of it. Okay, you know that the other value is greater than whatever stored, so this would be useful. Okay, there are some other overloads and utility functions, and Harris corner detector is part of them. Good, let's go back to our slides and let's continue with the Sift. Okay, the motivation for Sift is this. Okay, Harris operator corner detector is not invariant to scale, and the correlation, we have seen it. Correlation is not invariant to rotation. Remember the covariation. correlation, which is the expensive one. Harris operator is not invariant to scale, because if you scale your image, all of your C matrix changes and you're not going to find the same thing. Okay, so this guy, his name is David Lowe. Okay, this guy wanted to develop an interest operator, and he wanted to be scale and rotation invariant. If the scale changes, that's okay, I'm going to find it. If the rotation changes, that's okay, I'm going to match it. Okay, also he said that I am going to give you a descriptor. That means that after finding the key points, I will give you a good way of describing it, like the histogram that I showed you. And this descriptor is the one that you're going to use to match your points between the images. And in fact, this method ended up being used for the descriptor part for most of the time. Finding the key points were done using different techniques, but using the descriptor was common. Okay, so remember this picture that I showed you before? It was from the Sift paper or Sift tutorial. Okay, so Sift is going to give you the key points. Also, it will give you the orientation and the size of the key point too. Orientation, it will say that my orientation is this way. This one says that orientation is this way, this way, this way, this way. Also, they will specify the sizes of the key points. If you know the orientation and the sizes of the key points, I can normalize them. And whenever I find other key points in the other images, I can make these comparisons. Now you know what we mean by it is scale and rotation invariant. It is invariant because it knows the scale and the rotation. Okay, so I can map them to the same normalized images. Okay, so the advantages of Sift, it is locality, so it is distinctive. All the features are local. If the features are local, that means that I don't need to see the whole object. It's like Harris corner detector. Of course, it has to be distinctive. Whatever point it finds, you cannot find similar points around the same neighborhood. Quantity, Harris doesn't tell you, the Sift will not give you just 1 or 2 points per image. It will give you many points so that you can do your matching between the images. It is efficient. You can run Sift detector on your images in real time, 20 frames per second on regular hardware, and it is extensible. It could be used for color images. It could be used for gray level images. You could use it with different feature types. These are all advantages of Sift. So these are the steps of Harris corner, steps of Sift key point detection and the description phases. Scale space extrema detection. Remember we said that we don't depend on the scales anymore with the Sift. We are going to look at this one. This is new. We didn't have this step for the Harris. Then key point localization. This is similar to Harris. Okay. Then the orientation. I need to know about the orientation, rotation. So this makes the whole Sift operation scale invariant. This makes the Sift operation orientation invariant. This is similar to Harris corner detection. Then after that, I come up with a more than 100 element size vectors for each point. That will be the descriptor. So let's look at this first step. Scale space extrema detection. Okay. Scale space is this. This is your original image. Let's say this original image is 256 by 256. That's the size. Okay, I can produce a smaller version of this image by taking these 4 pixels in the corner and taking the average and putting it in the corner, right? So in effect, I am taking the averages of these 4 and putting in here. So my new image is going to be 128 by 128. If I continue this process, 64, 64, 32, 32. Okay, so this is an image pyramid. This is called image pyramid. Okay, so I expressed my images at different scales. Harris corner detector only worked on the original scale, didn't consider the smaller ones. Sift doesn't do that. Sift tries to see what is changing between this image and this image and this image and this image. That's what makes it scale independent. Okay, that's what makes it scale independent. So in this space, we are going to look for places where it is special for the special for the scale. Okay, so the goal is identify locations and scales that can be repeatedly assigned under different views. So I will make my search both X, Y, and scale dimension. Now I have 3 dimensions: X, Y, and scale. Okay, so my job is a little bit more difficult. I don't live in 1980s anymore. Okay, this is now 2000s. I have more CPU time to use, so I am going to turn into 3-dimensional search methods. Okay, search for stable features across multiple scales using continuous function of scale, and for that one I am going to use lambda, Gaussian lambda, Gaussian sigma, sorry. Okay, so I have now my images in X, Y, and sigma. Okay, X and Y are dimensions. Sigma is the scale dimension. It is the sigma of the Gaussian that I am going to apply. Okay, so how did you choose the sigma? I mean, where did the sigma come from? Some people in 1990s they did a work. If you are going to work in the scale space, then sigma is a good way of expressing this new direction, new dimension. Okay, so it is exactly what I am doing. Take the mean and put it in here. This is wrong. They should put in here, not there. Okay, so first apply the Gaussian filter with some sigma amount, then do this taking the median and produce it this way. Okay, so original image, second level, third level, and it goes that way. Good. Okay, we don't actually, this is the sigma. Okay, this is the image pyramid, but we don't use the pyramid as it is to find the special points within this pyramid. Okay, we use some other operators. Okay, and the motivation for the operators is they try to see the difference between this one and that one and that one. Whatever we are losing, whatever we are gaining by doing this. Okay, they are trying to look at it. But it looks like I am out of time. As I said before, I was going to leave you early because I didn't do the second break. I think I'm going to stop here. I have a meeting to attend. I will see you guys next week. Do you have any questions?
Can I ask a couple questions about one quickly?
Sure.
First is about the Jupyter notebooks. When the mouse event occurs, it crashes. So can we show it on different platform?
Does this happen for everybody?
Yes.
Okay.
No.
Okay, you can whatever. I mean, if as long as you can make your demo and you can prepare your report, that's fine. Whatever you can find as a solution.
Okay, the other question is, after converting the image to a top view image, are we done? So do we need to line the offside line?
No, I didn't ask you to do that. But if you do it, that would be nice.
Okay.
But I mean, it doesn't make much sense to draw the offside lines on the top view. If you like to draw the lines, okay, draw the lines on the original image.
Yeah, that's logical. Okay. And the final question is, we want to work with the an infinite point.
Yeah.
But these lines generally will intersect at some point. So how is that infinite? So am I just going to add 0 to third coordinate and this is infinite coordinates?
No, of course not. Parallel lines, okay, in your original image, most of the time they will intersect. But on your top view image, they will not.
But we don't work with top view image.
Yes, you do. Because the homography that you are trying to create is from the original image with the top view image, right? The parallel lines will intersect in a non-infinite position on your original images because of the perspective distortion, but those points will be transformed to an infinite point because in your top view image they intersect at the infinity.
After converting them, so we will try to find it.
No, how do you convert it without finding the homography? How do you find the homography?
So I've selected 4 points from the photos which I've taken from angles, right?
Yeah.
And after that, then I have another output points that I've already set. So the formula is there. So I'm just applying and getting the homography.
You should use the infinite point while you are getting your homography. That's what I asked.
Okay. Okay, I will search about it.
Okay.
Thank you.
But sir, the functions that you are suggesting to us doesn't work with the homogeneous coordinate.
Then in that case, you need to figure out it yourself. Use your formulas. Use your formulas yourself. Okay, I need to go, guys. Why didn't you ask this earlier?
Can we ask a little bit question in next week?
Sure, yeah.
Okay.
Okay, I'll see you later.